Today we will be discussing about electric flux denoted by phi. Electric flux is defined as the number of field line passes through a surface inside an electric field. Let us consider a region of electric field, a uniform electric field, and that is represented by parallel field lines as shown in this figure. And I am constructing an area perpendicular to the uniform electric field. Now certain number of field lines are passing through this particular surface, and the number or group of field lines passes through a particular surface is called electric flux. So actually it is defined as if the area is kept perpendicular to the field lines, then the flux is defined as the product of magnitude of electric field and area. So phi is equal to E into A, and therefore electric field from this equation can be written as E is equal to phi by A. So this can be considered as another definition for electric field. Electric field intensity, or simply electric field, is nothing but electric flux density. Means electric flux per unit area is equal to phi by A. This can be considered as another definition or another explanation for the concept electric field. Now we are going to discuss something in details about electric flux. For that, first we have to understand area vector. So you know area is a scalar, but sometimes in physics, most probably in electrostatics and magnetism, area can be considered as a vector. If area is considered as a vector, and a vector direction will be perpendicular to the area as shown in the figure. Let us consider a small area dA, then the area vector will be always perpendicular to the area like this. So area, if it is considered as a vector, then the area vector will be always perpendicular. Number two, sometimes the electric field will not be perpendicular to the area. There may be some inclination of electric field. In this case, you can see the area is like this perpendicular as in the previous case, but electric field is passing inclined. At that time, not the entire electric field is confined to that particular area. In this particular situation, let us consider a small elemental area as shown in the figure. Small elemental area, and that particular small elemental area is denoted by the letter ds. Now you can see area vector is perpendicular to the area. Area vector is denoted by ds vector. Now you can see the electric field direction is like this. There is an angle between electric field and area vector. Let it be theta. Now you can see the component of electric field in the direction of area vector is E cos theta only. Not entire electric field is in the direction of area vector. In the previous case, the entire electric field was in the direction of area vector, but in this case only component of electric field E cos theta is in the direction of area vector. In this type of situation, the flux is defined as the product of component of electric field in the direction of area vector and the magnitude of area vector. The component of electric field in the direction of area vector is E cos theta, and the magnitude of area vector is ds. Therefore d phi can be defined as E cos theta into ds. So that means E ds cos theta. Since E ds cos theta can be written as E dot ds, the flux through that surface is denoted by d phi is equal to E dot ds. So that means this is another definition for electric flux. Electric flux can be considered as the dot product of electric field and area vector. Once again, the definition of electric flux through any area is the dot product of electric field and area vector. Now, this equation gives a very small flux through a very small area ds. Now, our aim is to find the entire electric flux through the total area. So that can be obtained using the method of integration. So total flux phi is equal to integral over the surface E dot ds. So this equation can be considered as the total flux equation. So the electric flux through any surface is the surface integral of electric field over that surface. Once again, electric flux through any surface can be defined as the surface integral of electric field over that surface. Now let us discuss different cases of flux. Now you can see in this particular representation case 1, case 2, case 3. Three cases we are going to discuss. Case 1, electric field and area vector are parallel to each other. Means I am considering the area ds like this. Area vector will be perpendicular to the area, and electric field and area vector are parallel means the area is kept perpendicular to electric field. When area is kept perpendicular to electric field, area vector and electric field become parallel. That means theta is equal to 0, and the flux according to the definition, flux d phi is equal to E ds cos of 0. Cos of 0 is equal to 1, therefore d phi is equal to E ds maximum. So the flux through any surface is maximum when it is placed perpendicular to the electric field. Now case number 2, here electric field is like this, but area is kept parallel to the electric field so that area vector become perpendicular. When area vector and electric field are perpendicular to each other, then theta is equal to 90 degree. D phi is equal to E ds cos of 90. Cos of 90 is equal to 0, therefore d phi is equal to 0 means minimum. In this particular situation, when the electric field, when the area is kept parallel to the electric field, no field lines will pass through the surface. So it will just trace through the top of the surface and bottom of the surface. No field line will be cutting through the surface. Therefore, flux is equal to 0. The flux is the number of field lines cutting through the surface. In this particular situation, no field line will cut through the surface. Therefore, electric flux is equal to 0. Now you can see the case number 3. Here area is kept like this. The area vector is like this. Sorry, area vector is like this towards the positive x direction. But I am having an electric field which is opposite to the area vector in the negative x direction. Look at angle between electric field and area vector. Angle between electric field and area vector is 180 degree. Therefore, flux passing through this particular surface d phi is equal to E ds cos of 180. That means cos of 180 is equal to minus 1, therefore d phi is equal to minus E ds. Magnitude wise flux is maximum, but there is a negative sign. That means negative maximum. We will discuss this negative flux little later. Now look at the equations of flux once again. The flux can be written as phi is equal to E into ds, or phi is equal to E into A. First equation we studied. According to that equation, the unit of the flux you can see Newton meter square Coulomb raised to minus 1. Because Newton per Coulomb is the unit of electric field, meter square is a unit of area. Therefore, Newton meter square Coulomb raised to minus 1 is the unit of flux, or it can be written as voltmeter also. How it can be written as voltmeter? That's the next question that I can explain. Newton meter square can be written as meter into meter. Obviously, Coulomb raised to minus 1 means Newton meter into meter divided by Coulomb. Now you can see Newton meter. What is Newton meter? Force into displacement. Work done. Work done is denoted by joule. The unit of work done is joule. Therefore, it can be written as joule per Coulomb into meter. Now, what is work per charge? In the 10th standard you studied work per charge is nothing but volt. Therefore, joule per Coulomb into meter can be written as voltmeter. So altogether, unit of flux is Newton meter square Coulomb raised to minus 1, and that is equal to voltmeter.